What is going on, guys? Welcome back. In this video today we're going to train a large convolutional neural network to classify chest x-ray images of patients to predict whether they have pneumonia or not. We're going to go through the full machine learning process, we're going to train the model in the cloud, and we're going to deploy it to a serverless endpoint, and then we're also going to build a web application in order to interact with it. So let us get right into it. Alright, so this is going to be a quite comprehensive and interesting project today. We're going to do a lot of different things. It's going to be very versatile. We're going to load the data, we're going to train the model, we're going to train it in the cloud, which means we're going to interact with the server, we're going to set up things there, we're going to download the model weights, then we're going to build a handler and deploy it as a serverless endpoint. For this, we're going to use Docker, and then we're also going to build a web application to interact with this endpoint. So there are going to be a lot of parts, there are going to be a lot of different tasks. And also the training process is going to be maybe different than usual. We're going to use a pre-trained model. So we're going to do transfer learning because we're going to train an existing architecture with existing weights on our tasks. So you could say we're fine-tuning it or further training it on our data. And this is going to be quite, as I said, comprehensive, versatile, interesting. So I hope you stick around here. So the idea is, as I said, to classify chest x-ray images. We're going to use this data set here from Kaggle. You will find a link to it in the description down below. The basic idea is we have training, testing, validation data. And here we have two directories, normal and pneumonia. And the idea is to train the model to recognize the differences between normal x-rays and actually now I went to the wrong page. Normal x-rays and pneumonia, so when someone is sick. That is what our model should be able to do. And the interesting thing, as I said, is we're going to do all of this in the cloud. What's the idea behind doing it in the cloud? It's not necessary for this project because we don't have too large amounts of data. We don't have a too complicated architecture. But oftentimes you want to train something and you want to train it for many epochs. You have huge data sets. You have complicated, large model architectures. And it makes sense to do that in the cloud if you don't want to use your own resources, or maybe if you don't have your own resources or your own resources are not that fast. So some of you guys might not have a GPU. If you do all of that on the CPU, it's going to be quite difficult. And it makes sense to use GPUs for that. And it also makes sense to use powerful GPUs for that, especially if you have more data and more complicated architectures. Because of that, for this video today, I partnered up with RunPod, so they're the sponsor of this video, and this is basically an all-in-one cloud for AI. What we're going to do here, as I said, is we're going to train the model on their server. We're going to then download the model weights, we're going to build a handler, and we're going to deploy that again on RunPod as a serverless endpoint. And then we're going to build a Flask application. You can also build a Django or Fast API application, whatever you want, to interact with this serverless endpoint. So we're going to see how this ecosystem works. If you want to follow along with the tutorial, you can also do it on your own system. So you can train the model on your own system and you can run it as a Docker container on your own system. And then later on, if you want to, you can deploy it on RunPod. But this is what we're going to do in this video today. Now, before we get started, the last thing I want to mention is none of this is, of course, medical advice. This is just programming. This is just a machine learning tutorial. None of this is in any way to be considered a medical advice, or you shouldn't use that model for anything where you think it's going to make a difference medically. This is just a tutorial on programming. I need to say that as a disclaimer here. And now we're going to get started. The first thing, of course, is to download the data set. So we're going to go to the site. We're going to download it, in this case, as a zip file. I'm going to put it here into my current directory. I'm going to then go to this location. Okay, it's going to take some time, but we're going to jump to this current directory here. And we're going to write, first of all, the model training script. So we're going to write this locally because I like to use NeoVim and so on. And then we're going to connect this to the RunPod cloud. We're going to run the actual script there and get the model weights. So the first thing is the train model script. For this, of course, we need a couple of packages that maybe you don't have installed by default. So we're going to need to install using pip, of course, Torch, so PyTorch. We're going to need Torch Vision. we're going to need pillow, we're going to need scikit-learn. And I think actually for the training, that's all we need. So I'm going to run this. In this case, I already have everything installed. Or actually, it's going to, does it update Torch? I think so. And once you have all of this set up, once you have the data set and the packages installed, you can unzip the archive. So we're going to extract it here. And in here we have this chest X-ray directory. This is going to be our data directory. So it takes some time here to extract all of this. We have a bunch of images in here. But then I'm going to take this out. I don't want to have like this nested structure of archive and chest X-ray. I'm going to take this and put it directly into my current directory. We're also going to have to upload this to the server since we're going to train the model on the server. So it probably makes more sense to upload this as a zip file and then unzip it on the server, which we're going to do here. But for the training process now, let's wait until all of this is extracted and installed, and then we're going to write our training logic. Okay, so now everything is done. We're going to go into this. I'm going to cut this and paste it here. I'm going to delete this. I'm going to keep this because we're going to upload it to the server. And now I'm going to create a new file called train.model.py. And here we're going to define how our model should be trained. This is what we're going to execute in the cloud. And we're going to start with the import. So I'm going to say import OS. I'm going to say import torch. I'm going to say import torch.nn as nn. Import torch.optim as optim for the optimizers. Then from torch.utils.data, we're going to import data loader and also data set. And then we're going to also say from torch vision, import transforms and models. And then also maybe let's do that above. From pillow, we want to import image. And then maybe also from sklearn.metrics, we want to import the accuracy score. So these are going to be the imports for training the model. Then the important thing is, since we're going to run this on a server with a GPU, we could just go and say it's going to be all CUDA. But if you want to keep this flexible, what you want to do is you want to add this line. You want to say device is going to be torch.device. And we're going to say CUDA, which means it's going to use an NVIDIA GPU or a CUDA supported GPU, if torch.cuda.is available. So if there is a GPU that supports CUDA, use it. Otherwise, we're going to say CPU. So you can keep that on every system, which means that if you're running this on a laptop without any dedicated GPU or something, it's going to use CPU. And if you're running this on a server where you have a CUDA supported GPU, you're going to use CUDA. So you're going to use the GPU. Now what we're going to do is we're going to load our data set. And for this, we're going to create a class, which we're going to call Pneumonia Dataset. Or actually, we could call it X-ray dataset, but let's call it Pneumonia dataset. It's going to inherit from dataset. And in the constructor, so in the init method here, we're going to pass self, root directory, and transform, which by default is going to be none. And we're going to basically load 3 different data sets, the training, the testing, and the validation data set. We're going to say self.root directory is whatever we pass as a root directory. Self.transform is whatever we pass as a transform. This is going to be important because our model that we're going to use is called ResNet 18. So residual network 18. And yeah, you can look at the structure here. It has a bunch of convolutional layers, also some average pooling here in the end. But this requires a certain pre-processing. First of all, it requires a certain dimensionality, so a certain resolution, which is 224 times 224, but it also requires certain normalization with certain means and standard deviations. So this is why we need to take care of the transform. Then we're going to say self.imagePaths is going to be equal to an empty list. Here we're going to have all the images, and self.labels is going to be the classification. So what is it actually? Is it normal or is it pneumonia? And then now we're going to say for label in normal pneumonia, we're going to say class directory is going to be equal to os path join. And we're going to join now the root directory that we pass. This is going to be either the train, the test, or the validation directory. We're going to join that with the label. Why are we doing that? Because if we look at the data, we have the root directories here. So these three. And if I go into them, I have these two classes as directories. So this is how it's structured. And then I'm going to say for image name in os.list directory, class directory, we're going to say self.imagePaths append os path join class directory image name. So we're just getting all the paths to the images, and then for self.labels, we're going to append 0 if the label is equal to normal, else 1. So that is how we can create our data. Then we can implement some methods like the length dunder if we're interested in that. So to get the length of the data set, we're going to just return the length of self.imagePath or self.imagePaths. And then we're going to also, this is important, implement the getItem dunder. So how can we access individual items? For this, of course, we're going to get an index as input. And what we're going to do here is we're going to say the image path of the item is just going to be self.imagePaths at this index. Then we're going to load the image by using pillow. So we're going to say image open. So this is what we imported up here, pillow image open, image path. And then we're going to convert this to RGB. And then we're going to say the label for that is going to be self.labels at the same index. So they're going to be connected. And then if we have a transform, we're going to apply the transform. So we're going to say if self.transform, we want to say image is whatever this transformation is. So self.transform applied onto image. And then at the end, we're going to return a tuple of image and label. There you go. So that is our data set. Now we can turn this, or we can use data loaders to actually load the data set in batches, or the data from the data set in batches. But first of all, we're going to define our transformation. And this is, again, what we need for ResNet. This is not some arbitrary stuff that I just chose. This is what we need for the ResNet 18 architecture. So I'm going to say here, transform is equal to transforms.compose. So we're going to have multiple transforms, which is why we use compose. And the first one is going to be transforms.resize. We need to resize this to be 224 times 224. So remember, when we looked at the model, here we had an input of 224, 224. This is needed for this architecture. Then we're going to say transforms.toTensor. And then we're going to say transforms, and this is now the normalization. Normalize, and we need to pass here now mean equals, and these are the values now for ResNet, 0.485, 0.456, 0.406. And then standard deviations are going to be 0.229, 0.224, and 0.225. So this is just what we need for the architecture that we're going to use. All right, now let us create the data sets. We're going to say train data set is equal to pneumonia data set. We're going to pass as a root directory here. Actually, what is our folder called? Chest X-ray. So let's just call it. Actually, let's rename this to. Let's call this data. Root directory is going to be data and then train. And then I'm going to just say transform is equal to transform. And then we're going to copy paste this. We're going to replace train with test, and we're going to replace train with val, and the rest stays the same. And then what we're going to do is we're going to now create data loaders. So we want to load them in batches, and we'll want to shuffle the training data. So we're going to say train loader is equal to data loader based on the trained data set with a batch size of 32, and we want to have shuffle true for the training data. Then I'm going to copy paste this. I'm going to change this to test. I'm going to change this to test, and I'm going to set shuffle to false. Then I'm going to set this to validation. I'm going to set this to validation, and I'm going to set shuffle to false here as well. All right, so now we have the data sets, we have the data loaders. What we're going to do now is we're going to create a model, or we're going to actually load the model with pre-existing weights, and we're going to attach an additional fully connected layer onto it to get two outputs. So we're going to say here, model is equal to models.resnet18. And we're going to say that the weights we want to use here are equal to models.resnet18 underscore weights dot imagenet 1k version 1. So this is how we use the pre-trained model. This is a model that already is capable of a lot, even though it's not trained on our data set. And what we're going to do now is we're going to say model.fc is equal to nn linear. So actually we're just adding or changing this fully connected layer here to be model.fc in features. And the thing we change about this is we want to have two outputs. Why do we want to have two outputs? So that in the end we have the two neurons for normal and pneumonia. All right, and now what we're going to do is we're going to say the model should be sent to the device, which means we want to send it to the GPU if possible, because all the stuff that we work with has to be on the same device. We need to have all the data, all the models, we need to have them on the GPU if we want to work on a GPU. And then we're going to go into the training process. Now we're going to keep it simple here for the sake of this tutorial, but you can also extend this. I'm going to say number of epochs is going to be equal to 10, just so we can get this done somewhat quickly. So number of epochs is going to be 10, and then we're going to say for epoch in range num epochs, we're gonna set the model to training, and we're gonna say the running loss. Let me just recenter this. Actually, let me do it like this. Running loss is gonna be 0.0. So we're gonna always keep this. We're gonna always reset this at the beginning of an epoch, and then we're gonna say for image label, or actually for, since we're using a data loader, for images and labels in train loader, because we're getting 32 at once. We're going to say images have to be sent to the GPU as well, or to the device, whatever it is. Labels are going to also be sent to the device. And then we're going to zero out the gradients of the optimizer. So optimizer, actually, did we? Oh, we didn't create the loss function in the optimizer. Sorry, I forgot that. In between here, of course, we need to define that the loss function, so our criterion is going to be equal to cross entropy loss. Actually, yeah, we need to say NN cross entropy loss. And then we're going to say that our optimizer is going to be Atom. So optimizer is going to be Atom optimizer. Actually, it's going to be optim Atom. And we're going to set the learning rate equal to 0.001. And also we want to say that we want to train on all of the model's parameters, which means we're not just going to train a couple of layers, we're going to optimize, we're actually going to fine tune the whole model. Another thing that you could do is you could set all the layers to untrainable, and then you could set a couple of specific layers to maybe the top layers to trainable. That is also a strategy that can work sometimes even better. But we're just going to do this with all of the model's parameters, learning rate of 0.001. And here we're going to say now optimizer.0grad. And then we're going to say the outputs, so our predictions that the model makes, are going to be equal to the model applied to the images, and then we're going to compute the loss. It's going to be the criterion, not callable, criterion given the outputs and what the output should be, so the labels. And then we're going to say loss dot backward, so we're going to do the back propagation step. And we're going to do the gradient descent step, or actually the atom step, so optimizer step. And we're going to add the running loss. We're going to add this loss to the running loss. And at the end of each epoch, we want to print an f string where we're going to say epoch. And since we're going to start with 0, I'm going to say epoch plus 1 out of number of epochs. And then we're going to say the loss is whatever the running loss was, actually divided by the length of the train loader. So train loader, so that we get a good average here. Yeah, and that should be it. Then, of course, what we want to do is we want to also compute for each epoch the validation accuracy. So this is something that we do while training. Validation is happening while training. The test set will be evaluated afterwards, but we need to say here model.eval, which is also why we set it here to train again in the beginning, so that we jump back and forth between the two modes. So model.eval, we're going to say validation labels. They're going to be an empty list, and validation predictions are going to be an empty list. And then we're going to say with torch.nograd, since we're not training anything, we're just evaluating. For images and labels in validation loader, we're going to actually do not exactly the same thing, but I can actually copy at least these two things. So I'm going to send the two tensors to the device. Then we're going to say the outputs. So what our model thinks is true is going to be applying the model to images. We're going to say that the predictions are going to be equal to torch max, which means we're going to get the maximum output, the top output, so that we get only one value. And then we're going to say validation labels is going to be equal to, or actually extend, we want to extend the validation labels, which means we're going to add the list that we get to the labels. Is going to be labels.cpu, so taking it back to the CPU if it was on the GPU, turning it into a numpy array, so .numpy, and the same thing will be done for the predictions with the predictions here. And what we're going to do then is we're going to calculate the validation accuracy at the end. So we're going to say val accuracy is going to be equal to accuracy score from scikit-learn, val labels, and val predictions. And then we're going to print that. So we're going to say validation accuracy, and then val accuracy. That is that. And finally, we're going to also test the model. After the 10 epochs, we're going to evaluate it, and then we're going to output the model weights into a PyTorch file. So we're going to say here model evaluation mode again. We're going to say test labels is going to be an empty list. We're going to say test predictions is going to be an empty list. And actually this time we can copy the entire thing. So we're going to just, actually we can copy even this. So we can paste it down here. And we just need to change this here to test loader. This is fine. This is fine. And then here we need to change this to test labels. We need to change this here to test predictions. And then we need to change this here to test accuracy, test labels, test predictions, and to test accuracy, and here also test accuracy. The most important thing, of course, is to output the model weights, because we want to train them all in the cloud and download the resulting model weights so that we can use them for the handler that we're then going to deploy as a serverless endpoint. So we're going to say here torch.save model.state dictionary, and we're going to save it to the file pneumonia _classifier.pth. So that is our script. Let's see if I can even run this here. No, because of some CUDA stuff, but it doesn't really matter because we're not going to do this locally here. So we need to get this running on the server. How do we do that? What I need to do now is I need to go into run pod. And in the console here, we're going to create a storage. So you want to create a network volume. I already have one here because I don't want to upload all of the stuff again. But basically, you just create, you select the data center, you select the GPUs. You can see for each one which GPUs are available. You assign enough space to make this possible. And then what we want to do is we want to go to pods. So in run pod, you want to go to pods. You want to click on deploy. And you want to deploy, or actually we can do this here in the storage right away, deploy. I want to use GPU here, and we want to choose an available GPU. Right now, we can choose a 4090, for example. Oftentimes, you can also choose different ones. It depends on availability. You can also see the prices here. They're not very expensive. We can use this for less than 70 cents an hour. And what we're going to use is the PyTorch template. So this is already perfectly set up for PyTorch, which is what we're using. So we're going to use this template here. I'm going to say on demand. I want to have SSH terminal access, and I want to also have a Jupyter notebook. So I'm going to click on deploy on demand. This is going to take some while, and then we're going to upload our project, our training file, and also our data to the pod, to the storage. So I'm not sure even if my previously uploaded stuff is still going to be on the storage, because the pod is obviously destroyed and created every time, but the storage should be the same. So I hope that I will see my data still on there, but I'm going to still show you how to do that, how to upload your stuff properly. But yeah, what you're going to need is you're going to need a public key. So when we look at the pod here, I can open this up and I can click on connect. And what you see here now is that I can do a couple of things. I can start a web terminal. I can connect to Jupyter Lab, which is what we're going to do here also in a second. But what I'm interested in is connecting to SSH to set up stuff, or also to connect to expose TCP, because I want to use SCP, because I want to actually copy files to the server. So this is important, but for this I also need to have a key. So we need to configure a public key. Which means that we're going to run this SSH keygen command with our email address. And the important thing is you want to set this up as a public SSH key in your menu. Now, I'm not going to do this because I already have this, but what you would do here is you would, let's go, for example, to the desktop. Let's create a directory test key. And let's say here I'm running this SSH keygen command. -t ed25519 in this case, -c, and then some, I don't know, accounts neural9.com. Actually, I'm not sure if I have to use double quotations, so let's do that. Then I can just save it either here, or I'm going to save it in this case, my key here. I'm not going to use a passphrase. And now I have this my key and my key public. The important thing is I have to add them to the SSH directory, which I'm not going to do in this case here. And the public key, this is important. You want to copy paste the public key into the settings. So you want to actually see what the public key is. And in this case, it's that. I want to copy this, and I want to then paste it to settings, and then SSH public keys. I want to paste it here. I'm not going to go in here now because I have my keys here, even though the public key is not really important, but still. You want to paste it there, and then you can connect using this public key. So in my case now, what I'm going to do is I'm going to copy this command here, and I'm going to open up my terminal. I'm going to paste it, and this is going to allow me to connect to this pod. So right now, right here, come on. You can see that I am in the root directory. I also have here a workspace directory, and I still have my stuff here. So I already have the stuff. I'm going to still upload the train model again in case I made some mistakes while coding to make sure that this doesn't happen. But what I'm going to do now is I'm going to remove a couple of things here, the main notebook, and I'm going to also remove the model weights. So the Pneumonia Classifier, and I'm also going to remove the train model PY. I'm not going to remove the chest X-ray data because it just takes quite some time to upload it, but I'm going to show you what the commands look like. So you have this SSH command here, and you basically have to change it the following way. We want to go to our current directory, and I'm going to upload now the... actually, we don't need to upload, obviously, the weights because we're going to download the weights, but we need to upload the train model PY. So what we're going to do is we're going to say SCP, I think this stands for secure copy, -I, then we need to provide the key. This is the key that we just generated. So either you have it in the SSH folder or whatever, but in my case it's here, .ssh, and then ID _ ED25519, -P to specify the port that we're connecting to. We're connecting to, in this case, 40135, so 40135. And what I want to upload is the train model PY. Where do I want to upload it to? To root at, and then this IP address, 89.187.159.54, :/workspace/. This is what I want to do. Now I uploaded the models. So in my terminal, where is it? There you go. Here now I should see that I have the train model PY again. This is actually all we need to do. The same thing that you need to do here, or this is the same thing that you need to do for the chest ray zip. So you want to run the same command, but you want to do it with the archive.zip file. You want to upload it to this directory as well. Then what you want to do is on the pod, you want to run apt update to be able to see packages. And then you want to install, so apt install unzip. And then you just want to run unzip and then the archive zip file. And then you want to, create the structure so that you have this file. In this case here, we should rename, we should move chest X-ray to data, so that we have the correct name for our Python file. And now we're going to close this. We're actually not going to close this, but we're going to go into the UI here again. I'm going to click on connect, and I'm going to say connect to Jupyter Lab. So this is going to open up Jupyter Lab on the server, on the web interface, and I can see here my code that I wrote. So this is what we're going to use here, but I'm going to run this as a Jupyter notebook. So I'm going to actually copy paste all of this here. I'm going to paste it here. And one thing that we're going to change here, this is important. First of all, this is a PyTorch template, which means that we don't have to actually install PyTorch, but we still need to install, I think, scikit-learn and what was the other package? Pillow. So we need to say pip install, let me just zoom in a little bit here, pip install scikit-learn and pillow. You want to run this. And then we want to do one more thing to not make this slow. We want to use multiple workers in order to load the data. So what we need to do is we need to open up a new cell. We're going to say here import multiprocessing. And we're going to say multiprocessing.cpu, what was it? CPU count. And this is going to show you the available CPUs, even though they're probably virtual CPUs. And you want to use half of those to load your data. So I'm going to use 128 here as a num workers argument. I think num workers was the thing, right? Let me just check if that was the, yeah, I think it was num workers is going to be, oh, not here actually. This is why I don't get the suggestion. We need to do it here in the data loader. Num workers is going to be equal to 128. I don't have Vim bindings here, which is confusing. 128 and num workers equals 128. There you go. The rest should stay the same. So let's see if I can just run this or if I made some mistake. What should happen is it should download the model. So it should download the model weights. This should take some time, and then it should show us some information about the epochs. And then it shouldn't take too long to actually get to a decent result. So we get a loss here of 0.12, which is a validation accuracy of 75%. This is quite okay. Meanwhile, while this is training here, this is training on the server, so we don't have to care about the resources here. What we're going to talk about is how to actually turn this into a runpod handler. And for this, we're going to install a tool called the runpod CTL. So the instructions, actually, let me just copy paste a link here from my prepared notes. We're going to open this in a new tab. We need to install the CLI here to actually be able to work, or to actually be able to do this easily. So what we want to do is we want to install it using this command. I already have it on my system, so I can run here runpod CTL, and I already have the tool installed. But on Linux, you want to run this command to install it. On Windows, you want to run this command to install it. On Mac, you want to run this command to install it. And then the important thing is you want to generate API keys. So you want to go to runpod, you want to go to settings, you want to go to API keys, and you want to create a new API key here with read access. I think that should be, or actually no, I think we need also read and write access. So do that, create the key, copy the key, and then, yeah, actually it says you can choose both depending on what you want to do. I would go with read and write permissions. Click create and then run this command, runpod_ctl config -- API key, then the API key. This is going to authenticate yourself, or this is going to authenticate you with runpod, and then you can use the CLI tool to easily create and deploy applications. So that is what we need to do here. I'm not going to do these steps here. I'm going to do all the steps afterwards, but just go ahead, create an API key, run this command, and then you're good to go. And what we're going to do first while the model is training is we're going to go into our current directory again. I have a bunch of terminals opened up here, so let's actually get rid of this. Clear. What we're going to do here is we're going to run the command runpod CTL project create. This is for our serverless endpoint. So I'm going to call this now X-ray project. And I'm going to use the hello world template. I'm going to say the default CUDA version is fine. The default Python version is fine. And now I have here the X-ray project directory. And in here I have the following structure. I have, let me zoom in a little bit again. I have the builder directory. The only thing that's important in here is our requirements.txt file. So here I'm going to put all my dependencies. Right now we only have runpod. We also need stuff like PyTorch and so on. And the important thing is we have our source directory. In here we have our handler py. This is what we're going to use to make this into an actual endpoint that can take an image, that can return a classification, and then we're going to build an application that interacts with this endpoint. So let's see if our model is trained already. Yeah, we get a test accuracy of 88.9%. This is quite fine. So we should have now the Pneumonia Classifier PyTorch weights. So what we want to do is we want to download them to our, actually exactly to this directory, because we want to have the weights in the same directory as the handler. So what I'm going to do now is I'm going to say same command as before. Do we have it? There you go. Only difference being, now we're going to do it the other way around. Now we're going to download from the server. Oh, actually, this was too much. What was the port again? I didn't look at it now, so let's see what the port was. 4135. 4135. So from this Pneumonia Classifier PTH to the local Pneumonia Classifier PTH, download the file. There you go, we have it here now. And now we're going to implement our handler. So we're going to say that our handler py, and here now we need to do a lot of repetitive stuff. So we need to do the same stuff like defining the model, changing the output dimension, loading the weights that we trained, transforming again, defining the class names and so on. So we're going to say here import run pod. We're going to keep this the same. We're also going to import JSON. We're going to import base64. From IO, we're going to import bytes IO. So this is all core Python here. We're going to also import IO itself. We're going to, this is all the core Python side. We're going to also import now Torch. We're going to import torch.nn as an n. We're going to from Torch Vision import transforms and models again. Then, of course, don't forget to import from pillow the image. And besides that, is this everything we need? I think so. So these are the imports. And now we need to do the same thing as before. We need to say that we want to use the ResNet 18 model. So we're going to say model equals models ResNet 18. Weights are going to be none. And then we're going to say model fully connected is equal to nn linear. And we're going to say model fc in features 2 again. And now we load the weights that we trained. So model load state dictionary torch.load. And we want to load the source. This is important. You need to specify the path relative from the beginning. So from the project directory. So even though it's in the same directory as this file, this is not the file that we're actually running. So we're actually going into the source directory and then to the Pneumonia Classifier PTH. Map location is going to be torch.device. Actually, now I'm using CPU. Why am I using CPU? Oh, probably it doesn't really matter because for the inference, we don't really need to utilize the GPU. I think you could also do the same thing as before with the device. I chose for some reason to use the CPU here. Weights only equals false. And now we have our fine-tuned trained model ready to go. So we need to set it to evaluation mode since we're not training anymore. We're just doing inference. And we're going to define the same thing as before. Actually, let me use this from the file itself. So let's open this in a new tab. Let's copy this here and let's paste it here so I don't have to rewrite all of this again. It's going to be the same transformation as before. And the class names are, of course, still equal to normal and to pneumonia. So that is that. And now we're going to define a helper function called validate input. This is more of a thing for the application than if we send something that is not allowed or doesn't have the correct format. We're going to raise exceptions, or we're going to return that an error message that this is not possible. We're going to say, for example, if the input is none, we want to say that we want to return none, and the error message, please provide an image. Then we're going to say if is instance job input string, try to parse it. So job input equals JSON loads, so load string job input. If this fails, we're gonna if we get here a JSON decode error, we're gonna return none, invalid format or invalid JSON format, whatever you want to call this. And otherwise, we're gonna say here image data is equal to job input. Since now it's a JSON object, we're gonna get the image. So our input that we send, so our request that we send, will contain the field image and then a base 64 encoded string. So the image is going to be encoded as a string. We're going to say here, if the image data is none, we're going to return again none. Please provide an image again. And also, if not is instance image data string, we're going to say return none, image must be base 64 encoded string. And finally, if it is, we're going to say return image with image data. So this is just making sure that we have a base 64 encoded image. So this is just a helper function. You can also omit this if you're just going to provide valid input all the time, but this is now a helper function. And the handler is now where the magic happens, where the inference happens. So we're going to say here that the job input is going to be equal to job input. This is fine. We're going to keep that. Then we're going to say validated data and error message is going to be equal to validate input job input. We're going to get rid of all this. And then if we have an error message, we're not going to process it. So we're going to say if an error message exists, we're going to return error and the error message. And otherwise, we're going to get the base 64 encoded image. This is going to be equal to validated data image. This is important because when we transmit data via networks, we need to transmit them, or it's more convenient to transmit them as strings. So we want to base 64 encode them. So I'm going to say here image, image base 64, and then we're going to do a try. So we're going to try to get the bytes from the image. So we're going to say image bytes, and now we're going to use the base 64 package. So base 64 b64 decode image base 64. Now we have the image bytes. Then we want to create this to a pillow image, or we want to turn this into a pillow image. Actually, this needs to be equal. Image open bytes IO, image bytes, and we're going to convert this then again to RGB. Yeah, so this is how we load the image. Then we're going to apply the transformation. So image is going to be transform image so that we can feed it into our network again. And then we're going to also unsqueeze the image. So we're going to have the proper dimension with a batch so that we can feed it into the network. So we're going to say image.unsqueeze unsqueeze 0. And then we're going to run the inference. We're going to say with torch no gradients. The outputs is going to be equal to model applied onto the image. And then we're going to say nothing, and prediction is going to be equal to torch max outputs 1. So give me the 1 maximum value. And then the predicted class is going to be equal to class names predictions dot item. So that's going to give us the class. And in this case, what we're going to do is we're going to just return. So this is now a success. We're going to return prediction and then predicted class. That's that. We can have 3 errors here, or actually 2 errors and then everything else. So we can say except if we have a base 64.bin ASCII.error. That means that we can return error with the message that invalid base 64 encoding. If we get, on the other hand, a simple IO error. We're going to return error invalid image data. And in all other cases, so if we get any exception, we're going to just say exception as E. And we're going to say that we have an unexpected error. And this is going to be string version of E. And of course, we need to make this an F string. All right, so that's that. And the only thing that we need to do now is run pod serverless start. I like to actually have an if __ name equals __ main. I just like the syntax of this more so that we have this main entry section. And that is our handler. So this is our final endpoint that we're going to deploy now as a serverless endpoint. How do we actually do that? We do this in the following way. We go out of this direction into the project directory, and here now we run pod ctl project build. What this is going to do is it's going to create a Docker file. And actually, before we do that, I forgot one more thing. We need to export all the things. We need to export all the dependencies, all the requirements, or we need to at least put them into our requirements.txt file. So we want to go to the build directory. We want to go into this file here, and we want to say that we need, of course, Torch, we need Torch Vision, we need scikit-learn. Actually, do we need scikit-learn? Did we use it in the... We actually don't need scikit-learn, I think. But we're going to need pillow, we're going to need... Actually, I think that's enough. We need Torch Vision, we need Torch, we need pillow. These are the things that we use in our endpoint, so I'm going to just save this as a requirements.txt file. I'm going to go out of this here again, project, or run pod ctl project build. And what we have now is a Docker file. So if we look at this Docker file, we can see that we have here run pod, we have the requirements.txt file here, we have the handler py file and all that included. And what we're going to do now is we're going to exit that, and of course you need to have Docker on your system. So I'm going to run Docker desktop here just to have the engine running, and then we're going to actually build the image. So we're going to actually do a Docker build. And also, meanwhile, what you can do is you want to make sure that you have a Docker Hub repository where you can actually push this to. So Docker.io is the website. You want to sign up for this. It's completely free. You don't need to do anything. Actually, I think, am I using here? I think I'm using my Gmail here. Let's see. Yeah, so I have Docker Home, and then you want to go to Docker Hub. And I already have 2 test repositories for this tutorial here. So I'm going to create another one, create repository, neural9 repository name. Let's call this X-ray project. And make it public, create. And now I can upload to this repository here my Docker image that I'm going to create here. And then I'm going to just pull it into runpod to a serverless endpoint. That's going to be done quite easily. So let's see if my Docker engine is running. Seems like it is. So I'm going to be in that project here again where the Docker file is. And now I'm going to run the following command. I'm going to say docker build -- platform linux/amd64 -- tag. And this is now important. Here you want to use your Docker Hub stuff. So you want to use neural9 in my case. So -- tag neural9 / repository. So what's the repository that we created? X-ray project, and then :latest usually. So we built that image. What's the problem here? Requires, oh, sorry, we need to also provide dot for the current directory. And then it builds the Docker container. This is the thing that we're going to then push to Docker Hub. So it's going to do all the installations here. This is going to probably take some time. And once this is done, we're going to run the docker push command. We're going to have it at our Docker Hub uploaded. And then we're going to go into runpod. We're going to go to serverless. And we're going to create a new, actually, let me delete this endpoint here. These are some default names here. You want to click on new endpoint. You want to decide on a GPU. So I'm going to use this one, for example, here. You want to define max workers. And then what you want to do, the most important thing is you want to provide the image here. So in my case, this would be neural 9 slash, what was it? X-ray project latest. This is the thing that you need to make this possible. I would also assign something like 50 gigabytes, or just so you have enough space. And, or actually 50 is too much. Let's go with 20. I think that should be enough. But you can only do that once you've uploaded this. So we're going to wait for this to build, then we're going to push it, and then we're going to pull it over to the serverless endpoint. We're actually, instead of quitting this, what we're going to do is we're going to, not quitting this, instead of cutting this is what I wanted to say, instead of skipping this, we're going to actually start working on the Flask application. We can use this time, and we're going to do that in a separate directory. So I have too many terminals open up here. Here we have a fresh one. So let's go to the current directory again and create a directory. Let's call it X-ray underscore Flask. X-ray underscore Flask. And here now we're going to create an app.py file. And I'm going to maximize this. And of course, for this, no surprise, we need to also say pip install Flask if you don't have it. Or whatever you want to do. You can use Django, or you can use Fast API, whatever. You can even use a different programming language, because the endpoint is just the endpoint. You send requests to it, you get responses from it. You don't need Python anymore. So if you want to use Ruby on Rails or JavaScript, feel free to do that. But what we need here is import base64, import time, import requests, and from Flask import Flask render template and request. All right, and then we're going to create our application. We're going to say it's a Flask application with underscore underscore name underscore underscore, and we're going to have a single route, app.route, which is going to be the slash route. It's going to take two methods. It's going to have get and post as supported methods. And we want to keep this simple. We just want to have a simple website where I can upload an image, click on classify, and I get the response back. So I'm going to do it like this. I'm going to define upload. Actually, let's call this index. And we're going to say if the request.method equals post, we're going to do all of the logic. Otherwise, or actually we don't even need to do otherwise. I'm just going to say in the end here, we're going to return render template index.html, a file that we don't have yet. But that is what we're going to render by default. And then we're also going to render it, but with additional information once we have the classification. So what are we actually going to do if we post? So we're going to get from our HTML file an image file. So the file is going to be equal to request.files image. This is how we're going to pass the image. What we need to do now is we need to actually get the image data. So we need to say image data. We're going to encode it base64.b64 encode the content of the file. So take the bytes and encode them using base64 and then decode them with UTF-8. So this is the image data. And the important thing now is we need to say headers equals. And here now we need to authenticate ourselves. We need to get the authorization to the endpoint. How do we do that? We say authorization. And this points now to an API key. So here you want to put your API key again. It can actually be the same that we used before. So you go to settings again, API keys, you generate one, you use it. You can either do this as clear text, or what I'm going to do here is I'm going to say open API key read. Now I don't have this file yet, so I need to create it, which I'm going to do after a cut. But you need to load the API key. You need to pass it here as a header, and then we're going to say that the response is going to be equal to requests post. We're going to send a post request to our API, whatever it is. We don't have it yet. This is what we get when we create the serverless endpoint. So we don't have it yet, but we're going to send to this serverless endpoint some JSON data. And remember, our serverless endpoint, our handler, listens for input. So we're going to send the input, which is going to be image and image data. So to our serverless endpoint, to our handler, we send the input. The input is another dictionary with image pointing to image data. And to get authorization, we're going to say headers equals headers. And that should be working. Now let's see if actually our Docker image was built. It is so, or it was. So let's go ahead and push it to Docker Hub. We're going to say here Docker push neural9 / X-ray project latest. This is going to upload this. This is going to upload it. So we can wait for this to happen again. Let's just let it do the work. And here we're going to get now a response. Now the response is not going to be the classification. How this works with the serverless endpoint is you submit the request, you submit the thing that you want to classify, and as a response you get an ID of the job. And then you can check again later on if the job is finished. Now this doesn't take very long. It takes like 2 seconds or 3 seconds, but it doesn't work like this. It doesn't work like immediately. And because of that, we're going to say that what we actually want to do is we want to get the ID. So the res ID is going to be equal to response JSON ID. And we want to say we're going to allow for 10 retries. So for placeholder in range 10. We want to say that the status response is going to be requests post, and this now is going to go to a different endpoint of our API, which we're going to define later on. And we're going to say headers equals headers again. The important thing is, as part of our URL, we're going to also specify, so let's make this an F string, we're also going to have at the end our result ID or our job ID here. But what we want to do is we want to say status is equal to status response dot JSON, and we want to say if status dot get status lower, to make it case insensitive, is equal to completed. So if we have a classification ready, we're going to say the prediction is equal to status output prediction. And we're going to break out of the loop. Otherwise, we're going to wait, we're going to sleep for 2 seconds, and we're going to try again. We're going to do this 10 times, otherwise we're going to quit. You can also do this 20 times if you want to, but this is just going to allow the serverless endpoint to process the request before we just jump to the conclusion or jump to expect a prediction or just say we don't get a prediction. We're going to try a couple of times. And then in the end, what we want to do is we want to return, again, render template, index HTML. And we're going to say original image is equal to formatted string data image / JPEG, and then semicolon base 64 comma image data. And then we want to say the prediction is equal to the prediction. This is going to be stuff that we render now in the HTML file. The last thing before we go to the HTML file is if __ name _ is equal to _ main _ app run debug equals true. For now, for production, you should not have this as debug equals true, but that is our application. Now let me briefly check if our upload is done. Doesn't seem like that. We're still uploading, so it takes some time. So let us move on to the HTML file. Now the HTML file here is gonna be in a directory called templates. I'm gonna go here, I'm gonna create a file index.html. And in this file now, we're going to define the basic structure again, like doc type HTML, HTML. We're going to have the head section. And we're going to say in here, I'm going to actually copy paste the style part because I don't want to write this again. I don't like the styling. But you can either pause, or maybe I'm going to publish the code. So let me just, how do I do that? Let me do it like this. There you go. It's not too complicated. We just have a bunch of styling options here, margins and gaps and paddings. You can also just not do this. But the interesting part happens in the body. And what we're going to do here is we're going to say that we have a heading. And this heading is going to say upload image. And we're going to have a form down here. The method of this is going to be post. The name, or not the name, the encryption type is going to be equal to multi-part form data. We don't need an action because it's going to the same page, so it's automatically going to post to itself. And the input that we need here is going to be equal to, or it's going to be of type file. It's going to have the name image, which is what we're expecting on the back end. And we're going to accept here the image star or asterisk, which is basically all image types, and we're going to make this required. And then we're going to say line break, and we're going to have a simple submit button type submit, upload, and predict. It's going to be the text here. And that is our form. The only thing that we need here now is an if statement using the templating engine Ginger 2. If we have an original image and we have a prediction, what I'm going to do is the following. I want to display the image and I want to display the prediction. So I want to say diff, and in this diff here I want to have a heading 3 original, or let's say image. And then let's say image source is going to be equal to the string that we pass with the base64 encoding. Alternative, if for some reason we don't have it, I'm going to just say image. And then we also need a diff box down here. And let's just add a simple heading 3 with the prediction. And the prediction is going to be prediction. So that's not going to be a very beautiful application, but yeah, it will work, hopefully. So let's see if our upload is done. If not, we're going to just skip this. Okay, so now it's done. Let's go into the runpod serverless section again. Let's create a new endpoint. Let's use this one. Let's go and say container image is neural9/xray project and then latest, and that should be fine. Let's set this to 20, deploy. And if we didn't make any mistakes, which would be surprising as always, but what should happen now is it should download everything, it should build everything on the serverless endpoint, and then this is now the interesting thing is here we get the API endpoint. So in our Flask application, where was it again? Here, we had these API and API URLs. So what we need to do here now is we need to replace them with these URLs. So I want to use this one here to send the actual job. So to start the actual job, I'm going to just say that is the endpoint. And for the status, I have the status endpoint. So I have this one here, and you can see it takes an ID. So I want to go to this /ID. So I'm going to remove this. I'm going to paste this / and then res ID. And I also now added, even though it's not shown here right now. Why is it actually not shown? Okay, I actually do have an API key here, so I don't know why it doesn't show that. Maybe if I quit. Yeah, I do have the API key here. I'm not going to display it, obviously, but now it should actually work. So this is the full application. If we didn't do anything wrong. Worker is ready, so let's actually see if this works. So I can run this application. Cannot import name request. Oh yeah, you should spell request properly. And it seems like I also made the mistake here. So request, and I think also down here, requests in plural this time. And I think also that it's going to be a problem if I just read. Let's also strip any line breaks that I might have in the file. But besides that, this should work now. So let's run this. Opens up this server, and now I can choose a file. Let's go to our directory, to current data test, and let's go for some random pneumonia image, upload and predict. And this works, at least it is working. So let's see if we get a response here. Hopefully we get pneumonia. I'm happy about a response in general. There you go, prediction, pneumonia. We get the image, it says pneumonia. Let's go back. Let's try another one. Let's say this time data test normal. Let's go with this one here. Upload and predict. And it's not going to have 100% accuracy, so it could misclassify something, of course, but it had a pretty decent accuracy. There you go, normal. Okay, so that is how all of this works. We did 3 things now. We trained a model in the cloud, we got the weights, we deployed a handler to a serverless endpoint, and then now we have a Flask application that interacts with this endpoint. We used Docker, we used pre-trained models, so we did some transfer learning, and I think this was a quite comprehensive and interesting project. So yeah. So again, if you want to train models in the cloud, if you want to deploy models to the cloud, check out RunPod. You will find a link to them in the description down below. You would also support the channel by doing that. And as I mentioned, they're the sponsor of this video today. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.